Hello chemists, this is Ms. Placino and you are watching Screencast 3.1, an introduction to the periodic table. Chances are you're already pretty familiar with what the periodic table looks like. It is kind of the unofficial mascot of chemistry. Today we're going to talk about how that table is organized. There's a lot of reasons that the periodic table looks the way it does, and there's so much information that you can get simply by knowing where an element is located. So that's what we're going to focus on today, as well as look at some of the earlier contributions to the periodic table. If you could pause the video, go ahead and brainstorm things that you already know about the periodic table. I'm not going to take any time to go over the do now in this lesson, but hopefully as we're going through and talking about the periodic table, you can check things off your list and see how you're doing. I want to start off with some history on the periodic table. This gentleman is Dmitry Mendeleev. He is a Russian chemist and he's credited with creating the first periodic table, and this happened around 1869. By around this time in history, we've got about 60 or so of the elements discovered, and chemists are trying to find a way to organize and classify the elements. Dmitry chose to do this by taking essentially index cards and writing down the names of elements, their atomic mass, and properties, both chemical and physical, things like reactivity, color, density, so on and so forth. One thing to point out before we move forward, when we say atomic mass in this case, we're not talking about it in the way we know it today. Chemists don't know anything about protons or neutrons at this point in time. They don't have masses in AMUs. They've got relative atomic masses. So, for example, we know that carbon has a mass of 12 AMU today. There's no way they knew that in the 1860s. But they did know that it was 6 times heavier than hydrogen. Hydrogen, remember, is diatomic as an element, so it would be H2 with a mass of 2. So they don't know its exact mass, but they know, relatively speaking, how heavy it is compared to other elements. Anyway, Mendeleev took these little element cards and he started just arranging them in different patterns. And he noticed that when he arranged them in terms of increasing atomic mass and tried to keep elements of similar properties together, he started seeing some patterns. This is kind of how the first periodic table came to be. Mendeleev was very confident in his work, and he left holes in his periodic table. He made some predictions about what properties the elements that would go there would have. For example, he called one Ica aluminum, and he was able to predict pretty closely the properties of gallium, things like knowing it would have a very low melting point, and kind of being close on its density. So this technique of arranging in terms of similar properties and atomic mass proved to be fairly accurate, especially given the time period. If we fast forward about 40 or so years, we get to Henry Moseley. Moseley arranged elements by increasing atomic number. Again, at this point in time, in about 1913, we now have the nuclear model of the atom. Ernest Rutherford has conducted his gold foil experiment, and scientists are learning that essentially the charge of the nucleus is not only positive, but it's going to be different for different atoms. So if we go back to an example with carbon, carbon has 6 protons in its nucleus, so it has like a +6 nucleus. Something like oxygen has 8 protons in its nucleus, so it would have a +8 nucleus. So we don't really know what protons are just yet, but scientists are able to deduce that there is different magnitudes of positive charge in the different elements. He found that when he arranged by increasing atomic number, that you got to what's called the periodic law, which basically just means that properties of the elements are functions of their atomic numbers. And that's just the way the modern periodic table is arranged, in order of increasing atomic number. And we have kind of kept Dmitry Mendeleev's idea of keeping elements of similar properties grouped together. And really, as we study the periodic table, hopefully you see how all of this fits together. Let's get into the general organization of the table. We've got groups, which are the vertical columns. There are 18 of them in total, and sometimes they get called families. The way we're labeled here, we have group A elements, and we have group B elements. The periodic table that you have in your reference table doesn't lay them out this way. There's really no right way to do it. There's just kind of a matter of preference. I wanted to show you this one in case you come across other resources that you're not confused. So generally what we'll do is we'll just label them 1 through 18. Oops, got distracted. And I'm not going to go through and update all of them. I think you get the picture. The horizontal rows are called periods. That's these right here. If you think back to our previous unit when we were talking about electron configuration, if you think about the filling chart, we had 1s, 2s, all the way down to 7s, and then we never worried about like 8s or anything like that. And the reason for that is this only goes to 7. In theory, we could end up with, an 8th or a 9th or even a 10th different period in the periodic table, but our physicists are going to have to be much, much busier creating new elements. What I mean by that is actually like this periodic table fairly recently has been completed. We've been able to create man-made elements using particle colliders basically, and taking uranium and smashing other things into it to create super heavy elements that last for very brief periods of time. Another thing I'd like to point out has to do with these two rows of the periodic table that look like they've been split off and separated from the rest of the table. Some people mistakenly label these rows 8 and rows 9, but that's not actually true. If you take a look at the atomic numbers, starting in period 6, oops, look at that back there, we go 55, 56, 57, 70, 72. That doesn't seem to make any sense. In reality, this whole top row is supposed to get inserted right there. And it's going to stretch out the periodic table and make it 14 blocks wider than it already is. These are called the lanthanides, the bottom row, the actinides, and they're what we call collectively the rare earth elements. So occasionally you will see a periodic table where they've gone through and jammed these two rows into the periodic table where they actually belong, but more often than not you're going to see these two rows separated from the periodic table. Don't be confused, these are not periods 8 and 9. These are actually continuations of period 6 and period 7 respectively. What I'd like to talk about next is how location on the periodic table is going to give you some insight into different properties of that element. So let's look at a more simplified periodic table. And we've seen this one already back in Unit 1, but we'll go over it again just to make sure we're all on the same page. First thing I want to do is draw in my staircase, and that's basically just a zigzag line that starts up by boron and then kind of makes its way down through like a polonium. Staircase is what we're going to use as a point of reference. We know that metals are to the left of the staircase, with one glaring exception. Hydrogen is of course a non-metal, and it's just kind of in a bad spot. Nonmetals are to the right of the staircase. So these are nonmetals. Let's go ahead and label them. Nonmetals. Metals. Really no exception to our nonmetals. All of these are non-metallic elements. These purplish color elements that sit directly above or below the staircase are what we call the metalloids. You also might hear them called the semimetals. In order to be counted as a metalloid, you have to have two sides of that element box in contact with the staircase. So I'm just kind of highlighting the left and bottom side of boron in contact with the staircase, where something like phosphorus is just touching on that corner. There's no way that's going to count. Exception to this rule is aluminum. Aluminum looks, based on its location, that it should be a metalloid. However, aluminum is best classified as a metal. So those are our general kind of landmarks, and we can use that to figure out if an element is metallic or non-metallic, but be very aware of these two exceptions. Hydrogen is a non-metal, and aluminum is definitely a metal. So now that we've been reminded of the three general types of elements, I want to talk a little bit about their properties. Metals tend to be ductile, and what that means is that they can either be rolled or pulled into very thin wires. Think about like when your headphones fall apart and you look in there and you can see those really, really thin wires. Your wires are obviously made of metals. Metals are also malleable. They can be flattened out into thin sheets. Something like aluminum foil can be pressed really thin. Gold is super malleable. It can be pressed even thinner. Gold is surprisingly a soft metal, relatively speaking, and we actually have to spike it with other elements to make it stronger. So like when you get gold jewelry, there's a good chance that it is not 100% gold. It's too soft. Metals are also conductive of heat and electricity. Think about your frying pans at home. Chances are they're metallic. Metals tend to be shiny. They're going to be lustrous. Our metals are going to lose electrons and become cations when they react, especially when they react with non-metallic elements. And as we kind of showed you in that last slide, metals make up the vast majority of the periodic table, roughly 80%. Metals, or I should say non-metals, are like the complete opposite of metals. So whatever properties metals have, you can bet on non-metals being 180 degrees away from that. So metals are malleable and ductile. If you try to roll a non-metal or flatten it out into a thin sheet, it's just going to break. So we say that that means non-metals are brittle. Non-metals tend to be insulators, or at the very least poor conductors of heat and electricity. There are some exceptions to that. For example, pure carbon in the form of graphite does conduct electricity. That's why we make you fill out your bubble sheets with number 2 pencils. When we send them through the Scantron machine, it uses like an electrical current to figure out where you put your answers. But generally speaking, non-metallic elements are poor conductors, if not insulators, of heat and electricity. Non-metals are not shiny. We say they lack luster. From a reaction perspective, our nonmetals tend to gain electrons and become anions, especially when reacting with metals. And these are the elements that are technically classified as nonmetals. I wouldn't bother going through and trying to memorize them. Just use the general guideline of where the staircase is in the periodic table and know that everything to the right of the staircase is nonmetallic in nature. Finally, our semimetals and our metalloids, just like they're in the middle of the table, kind of that divider between the metals and the nonmetals, their properties are going to kind of reflect that. So some of them are going to have properties of metals, and some of them have properties of nonmetals. It's really element specific. We've got metals being conductors, nonmetals tend to be insulators, metalloids are semiconductors. Think about it. You have silicon computer chips. Silicon is a good example of a metalloid. Depending on what the element is, it can either be lustrous or lackluster. Metalloids are really flexible in a reaction environment. They can either gain or lose electrons. So you can imagine if a metalloid is reacting with a metal, metals always want to lose their electrons, so the metalloid will be flexible and gain. On the other hand, if they're reacting with a nonmetal, nonmetals always want to gain electrons, so the metalloids, again, will be flexible and this time lose electrons. This is the list of metalloids that I'd like you to know: boron, silicon, germanium, arsenic, antimony, and tellurium. Depending upon what resource you look at, sometimes like polonium or astatine gets classified as a metalloid. We don't classify them that way in this class. So again, these are our general properties of elements. So if I were to just give you an element, say chromium, you could find it on the periodic table. You could see that it is on the metallic side of the table, and you can give me some really general properties that you would expect chromium to have. Same thing if I went through and gave you selenium. You probably don't really know much about that as is, but if you find it on the non-metallic side of the periodic table, you can give me some pretty educated guesses about what its chemical and physical properties might be like. The last thing that I'd like to talk about has to do with this picture right here. For our purposes, most of our time will be spent studying the S block, which I'm circling, and the P block elements. Those are groups 1 and 2, and then 13 through 18. The D block, our transition metals, don't get a whole lot of attention in this level of chemistry course. When you look at the picture, hopefully one of the first things that jumps out at you is, wow, these are really brightly colored solutions. And that's what I'd like you to know about the transition metals. All of the well, I shouldn't say all, many of the transition metals, and again, that's groups 13 through 12, also known as the D block, are known for forming brightly colored compounds. So something like cobalt makes really pretty blue colors. You've seen rust before, that's an iron-containing compound. Manganese can be this really dark purple. And there's just many different colors that we can get due to those electrons in the D sublevel that kind of get moved around a little when we start to form bonds. So you don't need to know too much about the D block and the transition metals, just associate them with very brightly colored compounds. All right, that wraps up today's lesson. Take a minute or so to write a summary of today's lesson and make sure you feel comfortable with how the periodic table is arranged in terms of groups and periods, and that you start to familiarize yourself with the different general properties of metals, nonmetals, and metalloids. I hope this was helpful, and I'll see you again soon.